Hey, so I think finally I somehow managed to restart. It looks a bit weird. Um, but voila. So I think slowly we get it back here. So, so sorry for that. Um, so let's start very quick with our intro, and I first have to check that Ricardo is ready as a speaker. Where is he here? Voila. So, Ricardo, you should be back as speaker. Yeah, can't see or hear you yet, but
Yeah, now I'm
rest
in.
looks good. Okay, good.
Thanks a lot.
So, okay, sorry for that. We had a bit a challenge. We stopped the meeting too early and then you cannot restart it. I think this is something that I see for the first time that seems to be rather new with Teams, and also the help online was not very accurate. But anyway, let's start. I don't want to make it much longer. Calendar 2025, we have today the latest event, but we restart soon and end of January with the iBAT workshop on automation and robotics. To my latest knowledge, you can already register online. The agenda should be sent out before the end of this week with the more detailed program, but I think we have already quite a nice program with some international speaker, and we're just finalizing everything, and also to have the chance to visit Brucker in Fallanden, so to do a bit a site visit and also get in touch with all the people from ChemSpeed and from Brucker there. So would be nice to see many of you already early next year. Good. Then with that, I don't go in details for next year's program. I want to now finally introduce the Saleon AG, formerly known as Battery Consult. And with me today is Ricardo Tentella and Michael Bayer. And yeah, for the topics, it's mainly about who they are and what the technology they develop, and where they see the market fit, and the next step to implement them to or bring them onto the market. So with that, I'd like to hand over to Ricardo and Michael.
So thank you very much, Christian, for the introduction. Michael will just share the presentation in a few seconds. Here we can start.
That looks good.
Yeah, let's get started. So in these small particles that you see behind there, these granules made of salt and nickel, we do store energy in a sustainable way. So welcome to the presentation of Saleon. We will talk about the company and the technology more in detail. Today, I'm together with Michael Bayer. Unfortunately, Rebecca has a health issue, so wish her to get well soon. But today we will do it, Michael and myself. So what do we do? Basically, we do sustainable energy storage solutions, and we are located in the heart of Switzerland, in Meiringen. Our technology is based on sodium nickel chloride technology, and we have developed an own battery cell. You see it on the left side. So basically, it has a ceramic inside, which is a solid electrolyte, and we have on the outer part these granules made of salt and so ordinary salt, really, and the powder of nickel and some additives. But before we get into the technical details, let's say our claim is safe, solid, and sustainable, and everything we will try to explain that in this webinar today. Before we get started, who are we? In fact, our team is about 15 people that work in Meiringen, and you can just move on the next slide, Michael. Thank you. My name is Riccardo Dentella. I'm the managing director as an interim manager at Saleon. Rebecca Busch is our head of R&D, and she is covering all the chemistry parts. Torsten Korsinek is responsible for production and infrastructure. Michael is our scientist and physician. For the moment, he is head of the system integration team because we are in a very important step in our company. And Andrea is completing the team for the communication side. The challenge we address, basically, it's a challenge that in this community is very well known. So it's not a question about the energy quantity, but to have the energy at the right moment, at the right place, and to this critical gap between power generation and real-time use is driving or threatening the industries and critical infrastructures, and therefore also the energy transition. So I think this is very, very general for the whole battery industry. We are convinced that salt can really deliver in this context as a safe and reliable energy solution. If you look a little bit more in the value proposition of our technology, our value proposition at a glance, as I said, safe, solid, sustainable. The three keywords we put on top of our technology. Let's start with sustainable first. We have while this battery is basically made from salt, nickel, and ceramic, so there is no toxic ingredients in it. We have no critical materials beside the base materials, and also no persistent chemicals like PFAS or anything else. And many recycling processes are very well established, like for example for nickel. On the solid side, we have the reliable performance, so it's a very robust and durable design. It's engineered for the long-term efficiency with low maintenance, and we expect a lifetime of this battery technology more than 15 years. As far as we have studied, so there with a good treatment of the battery, nearly no degradation is visible over a very long time. And last but not least, from the three keywords, safe. It's a safe technology because this really the technology inherent in the technology is that it's non-flammable, it's non-explosive, and therefore there has a lot of safety attributes in it. It is a technology that operates at about 300 degrees, and therefore, so the outer temperature is not so really relevant for this technology, whether it's -20 degrees or +100. So it's more the challenge to adapt the electronics part in relation to the application, but for the battery itself, it's absolutely no issue. So this is a big point on the plus side. We're pushing a lot for the European value chain to minimize also the geopolitical risks. And yeah, you see also that on the right side, there's still some blank space. So there's one additional point to make is that we have a very easy scalable production. So generally in the battery technology, we have these gigafactories centralized somewhere in the world. Our technology is really based on basic technologies like laser welding, like mixing procedures, chemical processes of infiltration, and so on. So the baking of the ceramics, all these are, let's say, basic technologies. We can integrate strategically local partners for chemistry and ceramics. And this enables us to really to scale on a global scale in a decentralized way. So basically, another way said we can build a plant. So typical plant for a salt battery is about 100 megawatt hours to 300 megawatt hours. So we can build a plant in the country or in the region where we have really the demand. So we see this as a really, really big advantage in our technology. Well, Christian already mentioned that. So Saleon is not completely new. It's a company that exists for, the former company, Battery Consult, was founded in 2008, so more than 15 years. And our founder, Kurt Dustmann, he was already in this technology, in the Zebra technology, for about more than 20 years before. So he was also in Ticino. He was head of the production line, and then founded in 2008 the Battery Consult to develop new cell designs. In the first years, in the first decade, mainly together with South American energy company, Itaipu, because they have some close links with the KWO in Meiringen. This is also the reason why the company moved to Meiringen. And then over the years, all the technology, all the know-how that has been developed concluded then in 2020 in the design of our new and our recent cell, the STC 140 with 140 ampere hours there. So we have had then new ownership with Salinova starting in 2023, and we started to get this technology ready for a market entry. And we realized that the Battery Consult is not really a good brand name to get into the market, and this is the reason why we decided to to change the name to Saleon, a name which is composed of a salt part, salt or sale, and energy on. So in this kind of to make a link really where we want to go. You see on top of the list, I probably can move on the next slide. There we see the track record of Battery Consult until the end of December last year. How many cells have been built? More than 1,600 cells and different cell designs have been built over the years, over nearly, let's say, 17 years. About 76 test modules have been built and operated, and 17 prototype batteries. In the beginning, these were more the smaller systems with 7 kilowatt hours, and then this finally led to the first industry module by end of last year. This industry module has 140 cells in it. We will see some results, some recent results of this industry module in a later part of the presentation. But to give you an order of size, this is a 42 kilowatt hours module. So it's about 500 kilograms. So it's really a big and a solid battery, right? So this is really a big heritage that we have put into the Saleon, and we will go more in the technical parts later on. But before we go there, let's have a look what the market fit, or what do we find interesting on the market. In general, we refer to a business, let's say a market study from McKinsey. There are mainly one reason, because there is the commercial and industry part is separated and shows also a very interesting growth. If you see there, this blue part goes up to 60 gigawatt hours annual installed capacity in 2030. And we're really heading to the commercial and industry sector with our technology, where we can also mark points with our sustainability advantages. So our global playground, we will not go, let's say, we're not the only ones in the world that are, let's say, developing and producing molten salt batteries. There are different technologies. The original technology was sodium sulfur. NGK in Japan is producing that. Or there is the technology with the Zebra cells, like two Chinese players are producing, and the other Swiss company, Horion, is producing that. And there are some other technologies like Inlight, which are slightly different with sodium iron chloride battery. More or less, they are somehow similar, I would say. This is the reason why we don't call them competitors. For us, they are co-promoters, because I think there is really a nice niche market for this kind of batteries we want to head for. Which means, well, today when we talk about batteries, it's mainly we talk about lithium batteries. And yeah, Michael, just give me the next slide. Thank you. Our global playground is really there where, let's say, other battery technologies are, let's say, a little bit less suitable. So really, if you have some very sustainability-driven projects, or if you have very demanding climate conditions, very hot or very cold temperatures, the battery can be a very good opportunity. And yeah, so we are heading for industrial and commercial applications, as I already mentioned. We see also a big opportunity in decentralized industrial grids, because this technology, what we offer, you don't need to place them outside the production buildings. You can really place that close to the production lines or the robot centers. And we see also some very interesting opportunities for critical infrastructures. And critical infrastructures is a very large, let's say, field, starting from, let's say, telecommunication, which is more classical, but goes down to cold chains in hotels and so on. So it is really everywhere where this matters, really to support and to give a part of autonomy. So a salt battery is a little bit, let's say, it's not the fastest battery on the market, but it has its value in stationary applications, and this is where we see really a nice market fit for our technology. For sure, we can't go there with a small team of 15 people in Meiringen. If you see the global players, these are very, very big companies. But we have a very interesting network. We have a ceramics partner in Germany, Alumina Systems, who is also producing the cells for us. We have then on the salt side, a very interesting strategic partnership with the Swiss Saltworks, the Schweizer Salinen. And we're working on them. We have some development activities with them for the granules and the melt that we need. And we're also working together with PowerBlocks. PowerBlocks is our sister company, is owned by the same shareholder, Salinova, and they support us on the business and strategic development side, and also, let's say, the studies for potential customers. Yeah, why is Saleon really, let's say, a big opportunity, an interesting company? I already mentioned in our foundation and our basement, if you want, the strong partnerships, the Swiss innovation part. We have a lot of innovation, a lot of know-how put in, and we have also some interesting research partners like EMPA, the Swiss Innovation Park in Vienna, and the Fachhochschule Ost. We have very strong people, strong values, decades of experience. So the owner or the founder, Kurt Dussmann, is still passing by every day to have a cup of tea or coffee with us, really to transfer all this know-how to the staff. And also Michael, for example, is in this company for more than 15 years already. So we have a very, very profound understanding of the salt battery technology. And yeah, furthermore, we have already talked about the focused market strategy, commercial industry, and sustainability is getting more and more important for the customers in these markets. And we have also let's say, a very tangible roadmap that we will go to with the demonstrator on tour during next year, early next year. But last point is, in our point of view, the collaborative modular product strategy with these advanced cell design and the reliable systems. and this, let's say, straightforward scale-up. But to better understand this clever and modern product strategy, we need to a little bit more deep dive in the technical part. And this is the point where I want to hand over to Michael. He will guide us through the developments we have done on salt battery technology in the recent years and lead you to the products that we will bring to the market. So please, Michael, take over here.
Okay. Thank you, Ricardo, for what you have presented so far. I have now the honor to introduce you into the more technical details. Of course, we cannot go into everywhere, but I try my best. First, I want to show is the product in more detail that's really designed at Saleon. Basically, we have 2 cells, all based on sodium nickel chloride technology. When we started development, one of the goals was to reduce the cost per kilowatt hour. It's still one of the central goals. Yeah. And the approach is a very classical one. We increase the capacity. So basically, we have designed a cell which has 250 ampere hours, and but it turned out it has a discharge rate of 12 hours. All other parameters are more or less the same. We reach with this cell 530 watt hours of energy in the cells, and yeah, it's all based on a tubular design. The other cell is we decided that the market, which is there for batteries in the stationary sector, requests more the 4-hour discharge rates, and so we had the other cell, this 140 ampere hour cell, which brings the discharge rates to 4 hours, but the energy is down to 318 watt hours. The special thing about these designs is we use the same ceramic subassembly for both of the cells, the same seal technology, and the same negative electrode. So basically, when we designed the factory, it was always planned that we can change from one cell to the other within 2 hours. In fact, we don't have a big factory yet, but it's in the prototype manufacturing. It's possible, yeah. And so basically, when we really need the power for daily cycling based applications, we use the STC140, which is something like our standard product at the moment. And when really long-range energy storage capacity is relevant and autonomy is the key, we can use the STC250. Let's dive a bit into salt battery technology. It's since it's a bit different from lithium-ion technology. At the end, we are a ceramic-supported design. It's a solid separator made from beta aluminate. The basic redox reaction that takes place is that nickel and sodium chloride are reversibly transformed into nickel chloride and sodium. We all do this at a temperature of 300 degrees, which means the sodium is liquid. We thereby bypass any issue with the dendrite forming of solid dendrites. The OCV is quite solid. It's 2.58 volts compared to the single electron lithium-ion technology. It's low, but it's better than what you reach with nickel metal hydride. So I'm quite positive about the potential. And one of the big advantages is the technology is not only safe for the customer, it's also safe for the manufacturer. We produce the battery in a completely discharged state, so we don't handle any sodium in the manufacturing. We have a full control of the capacity with the sodium chloride, which we put in there. And one of the advantages I see is that also during handling, none of the components we are handling is basically inflammable. So we have a non-inflammable system. And in the 15 years for me working here, I'm really happy we have this. It really makes me feel comfortable, yeah. And enables what Ricardo says before, that the facilities can be built comparably small. One of the big things we have to do when you make a cell that operates at 300 degrees, you need a sealing technology that allows you to close the cell, even though you have the high operating temperatures. polymeric seals, which might be the standard solution for many of the sealings, are not a real option here. So what we have developed in the first years is this glass compression seal. It's based on a single furnace process. The other designs often use thermal compression bonding and subsequent ceramic seals with the glass, and we make all the seal in a single furnace process. But still, it takes 8 hours at 1000 degrees, so it's still some time. And so we have actually running at the moment this project where we are joining where we try to join at room temperature with a laser. I've talked about this on the annual conference. It was just for whoever was there. It's a reminder that that we talked about this. Okay, this is the LISA project. It's funded by the InnoSwiss. And we do it together with Empire and the Swiss Innovation Park in Biel. Good. The thing is, Ricardo showed you already the track record of the cells we built. We did not only build them, we also tested them, which gives us the trust in the technology. Of course, at the beginning, you have some challenges. There are 2 challenges. The first challenge is you reach the values you promised, and the second challenge is you reach always the values you promised. And so what I show now are mostly the results that we had from module testing. So it's not only reaching your goal once, it's reaching your goal always. What I can say is, on the left-hand side, it's the charging curves, the SOC over the time. And we promised in the data sheet that we will be able to charge the battery in 11 hours. And we reached it. Yeah. The data sheet performance values are generally well achieved, and the cell reproducibility, it's more shown on the right, is very good for us. So we have a very low, comparatively low voltage spread. The small spreading at the end of charge is because we go to really low charging currents and a really high cell resistance. It's not something that bothers me too much. And what is good for us, we also shown that the BMS we have developed in-house, it's running running stable, and we have a very convenient data logging, making life very easy for us. But what we found out is also not changing your cell design does not change your chemistry. So what we have to do is we need a full charge in a regular frequency, about once a week, maybe once every 10 days. And so this way, I will show you later how we will resolve this by our stack system. There's still, when I'm here after 15 years, something that's really enthusiastic for me about software technology, and this is an extremely high cycling stability. Of course, if you build cells that are designed to make 1 cycle a day, proving 10,000 cycles will take you more than 20 years. I don't have the time to do this, and so we have these small test cells, these FPC45 cells, and with this we can make quite high cycling rates. On them, we have proven in cells that we can achieve more than 10,000 60% cycles. Why we did 60% cycles is not because the cells are very unstable when you make full cycles. They even love it to make full cycles. But as we have seen before, I might go back. Going into details of charging, it takes some time. So we just in the accelerated cycles we try to prevent these tails. Okay. But every 100 cycles, we did the full characterization cycles with C/3 charging and discharging. Shown in the graph is the status of health, the energetic state of health, related to our promised value of 380 watt-hours at 950 grams. And what we see is that over 10,000 of these cycles, there was not a decay of the state of health below the 100% marker. Okay. So now we have to trust in the technology, in the chemistry. That's where we have, and now is the question how you come to build a battery system. our journey there, I always support the argumentation a bit with the penguins. It's what we call the Saleon penguin analogy. When we started, we preferred a bit the small systems. It gives less risk to you. You have a big market of private customers. But these systems are quite small. They have a few kilowatts, few kilowatt hours, and this results in small batteries. And as we remember, we are very warm guy, as the penguin has the same temperature as I have, and outside it's very cold. So we have 300 inside, and outside it's even if it's 50 degrees centigrade, it's very cold. And we don't like it that it's very cold. The advantages of the system are good. It needs to be integrated. We don't want to have noises for private customers. So it was very challenging for small systems. We would need vacuum insulation and a very minimal surface, and the result was, but it's no longer sold. The result was a capsule, more or less. Yeah. But if you change it over to the big emperor penguins, things might change. You have now many kilowatt hours. We can build very large batteries. At the end, you're very hot, and that is what we love. You have a very low surface per volume. And this might even change a challenge we had on the small system side to an opportunity. Because when the systems become very big, the cooling might become necessary. And if you are operating at 300 degrees, cooling is very easy at the end. You can just put in any air you find, and it's still very cold compared to the operating temperature. And you can even set the cooling as such that the output heat is at a higher energy level. So we have not thought it at the end, but there is a possible use for the heat. And what do the penguins, when it gets really cold? They form colonies. And so this advantage that we have with a bigger module becomes even more profound when we change to big battery systems, as it's illustrated here for container systems, for example. We have built such a module, and we tested it. This what we see here is the current profile over several days. It was in the midst of July. Yeah. We tested the realistic environment for the industrial module, and we coupled it to the 28 kilowatt power solar energy system, and with the internal consumers. So it was the goal to optimize the self-consumption of our facility. The system did quite well here. Of course, the cycling was a bit to get the full cycles, but as you see on the oscillations in the current, it was very well reacting to the changes in the power from the consumers and from the producers. We showed more than 100 cycles. This was something we did in a project with Klimastiftung Schweiz. And also in this module, we have seen the same as we have seen in the single cells. This energetic state of health stayed above 100% over all the testing period. But why do we need to cycle the big modules really? Only to show that we have 140 cells that are identical enough that we can cycle them without any balances, I have to say. So there's no electronic balancing between the cells. No, we have to show that the high temperature is not negatively interfering with our overall efficiency, and that's what is shown in the graph. The violet points are the state of health, and the green squares are the electric efficiency, and the blue circles are the total efficiency. So taking into account the heating, as we see, they are not really diverging too much. It's about 1% difference, and this is the heritage from the heat up. They even the gap gets smaller. Yeah. So what turned out that we effectively didn't need any heating during the normal operation of this module. So the high temperature was not interfering with the efficiency. And the overall efficiency was about 86% with the heating losses taken into account. So with all the data we had giving us confidence into the module and giving us confidence into the cell, which products are we going to bring to the market? As we said before, single batteries, we need this full charge about once a week. So this will make the customer not very happy. If the battery says once a week, hey, I need about half a day to charge me, please provide me with energy. That's not necessarily what I can easily sell to a customer. And so our minimal product we have produced is a stack that consists of 3 individual modules. The coupling between the modules is done by a DC microgrid that's operating between 700 and 900 volts. At the end, with this stack, we get a rated energy of 125 kilowatt hours as they come from the 3 industrial modules. We have a discharge power on the AC side of the full range of the capacity of 25 kilowatts. And on the DC side, we can provide for 15 minutes 50 kilowatts. Making the things big gives you already the first things about the penguin colony. We can keep the thermal losses quite low. And in the stack, we also demonstrate an air cooling system that I always say it's more or less adapting the isolation. You know? So if you have a high cycling performance, you can increase the heat losses as you requested to prevent an overheating of the system and keep full availability. Good. It's not only an idea what we have. The picture we have here is from a workshop. It was a few days ago. And it's really, when the thing is put into a material, it's a really exciting moment, I think, for a developer. And it's at the end, it's exciting for me as the product evolves. Yeah, and we will, by the end of the week, have it in our place and show and test it for the performance. Good. At the end, we have to open the mind even further. Yeah? It was always a plan, and it's still there. You have to make the product scalable. You have the modules, yeah, but they cannot operate alone. So the next thing is we will couple several of these systems to a operating system, which we call you call the stack pool 4x3. The plan is really to have a 500 kilowatt hour system, and we will then have a separate electronic compartment where we can integrate up to 125 kilowatts of AC/DC conversion. And it's really the idea to demonstrate this technology to the people and get the transition from the technology validation into the market acceptance. And this is what the big challenge we have for 2026, really getting the products and the customers together. At the end, the idea is here, the modularity. Yeah? If the cells go into a module, the module can go into a stack, it can go into the stack pool. At the end, you cannot build battery systems without the people asking you, and what about containers? No problem. You can take 48 of these modules and put them into a 20-foot containers. Of course, this means you have to build the 48 modules. And we have planned this container size, and then we turn out to arrive at about 2 megawatt hours at a discharge rate of maximum discharge rate of 500 kilowatts. it's a bit strange that the efficiency might increase, but it's because the penguins sticking together in the pack, they reduce the thermal losses under all circumstances. But I think with the container, showing the idea of the container, which is not for 2026, I think it's more for 2027, I can pass over to the question section and to Ricardo again.
Yeah, just to round up, thank you very, very much, Michael, for the presentation. I think we want to just to pass over this feeling in the face our company is. So we have a big heritage of battery consult, and this was a very, very fascinating year this year to transform this heritage into concrete products. And I think the next year is even more interesting because really want to go to the market and bring this product, the sustainable energy storage systems to the customers. You felt also the passion of Michael in this in our company, so we can really say energy is close to our heart. And yeah, we are happy to some questions if there are some questions in the round there.
Yeah, as usual, please just write the questions in the chat or raise your hand so we can open the microphone for you. Yeah, like lithium-ion batteries have become in the past very cost competitive. I actually read today that in China the price for lithium iron phosphate will rise up a bit per ton. I think around roughly 10% or something. So maybe we reached a bit the bottom line for now. But do you have any idea? I mean, you spoke about your concept in production, more a decentralized concept, but yeah, the competition is huge. And do you have an idea on how to compete against this established technology?
Yeah, absolutely. So it's so the price is a little bit difficult. For sure, we have made all the calculations and so on when you have really scaled up to a 300 megawatt hour factory. But all the prices that we have, they will, for the moment, be higher than the lowest prices of lithium products. So therefore, we're really heading for niche applications, applications where you have difficulties with other technologies because you can't put some battery systems into the production plant and actually, or if you are, let's say, in some critical environment, sometimes you don't want to have let's say additional, I don't use brandlast and burn loads. I don't know whether it's the right translation, but there are some safety reasons that can lead to that. And what we see in the discussions with potential customers is that also the sustainability aspect is really growing in value also somehow. But for sure, the systems will, for the moment, or also for the next 3 to 5 years, have a premium over the other battery systems and the current prices. And nobody really knows in which direction it goes. What we know is that we are not so much dependent on the prices. So yes, we are dependent from the nickel price, but let's say the proportion of nickel used today should be not a real issue. And yeah, also salt, we have a lot of salt available for our batteries. We don't need that much salt for one battery cell. So therefore, I think there is a big potential for that. But for sure, yes, the price question, I think we need to scale up. So we are really in this phase, and the next 3 years will really show where we want to go. What we can say today is that there are other battery systems based on salt that already on the market, and yet we are really in an early stage able to be at a lower price than let's say the more traditional battery systems, because we need for 1 kilowatt hours we need actually just 3 cells, whereas the classical Zebra cell needs 10 cells for 1 kilowatt hours. And so this is where we get an advantage on the production side, and we should be already in a small scale up, already possible to to be on a lower price or competitive price with other salt batteries. The rest is a little bit too early to state for the moment.
Okay. I see, for example, from Dirk Schneider, he asked in the chat with 84% efficiency, you are below LFP, 92 apparently, but above lead acid, about 80. Do you see a key target to replace existing UPS solutions in critical applications? I think this is maybe a bit what you explained, zero tolerance on safety. And then how would you compare to price? I think you don't need to answer that again, but maybe about the UPS is an interesting question.
Yeah, UPS. So when we're talking about critical infrastructure, we're not directly talking about UPS, because first of all, there are some dedicated and certified systems that are available on the market that covers this, let's say, this first intervention. We see us more on a backup, let's say after 5 minutes or so, that we can really support on a longer term. Because, if you have a new technology and bring it to the market, so really this proof, to compete with companies that have more than 20 years experience with their system in UPS, it's nearly impossible. So for sure, one day this will be on our roadmap, but not on the beginning. But I think in the second row, we see a big opportunity to do that. Yeah.
And then I think from Amira Abu Hamdan, I think this is more, I think a statement than a question coming from R&D. I'm curious about the journey from research to commercialization, TRL progress. Thanks in advance. But I think you basically showed a bit today how the commercialization strategy. But that's at least the way I understand, but maybe you understand it differently.
Yeah, I see that it's the same way. Well, it's a tough way to go. So really, it's a big transformation. Also in the heads of all the workers that we have, all the technical stuff. It's a big transformation from research to, let's say, a customer-oriented organization, and we're just in the middle of it. So I think we still need 1 year to really prove that we managed it to the market, right?
And then I have Mark from Hugo Brown. How important is the 20% higher energy from the energy container compared to the power container? Would it be possible to cover most of the applications with the power container?
I think this refers to the container, because we have 2 different systems. And if you have paid attention, it's the same design, it's the same construction. The only different thing is that that one container, which is more, let's say, more oriented on energy storage, has the STC 250. This has a C rate of 12 hours. So C divided by 12. Whereas the power container has the faster cell. So it depends now the application that you have. I think in many cases, I think you're right, that basically you can cover everything with the power. But in general, when you're going to autonomous, let's say telecommunication systems, needs today an autonomy of 48 hours or 72 hours. So you don't necessarily need the power container. So this is a little bit it depends on the application. It's more the application than it's really a product that adapts to the need of the customers.
Maybe I can add something which was maybe not very clear from the presentation. The power container is much more flexible, yeah. So, but it contains also more about the 2,000 more cells. So this means the energy container will be cheaper. So you can do it with the power container. It costs you about this 20% in energy, but you cannot get a power container for the same price as you have the energy container. As the number of cells is just bigger. Yeah. Okay. Thanks.
Okay, then we have Daniel Landmann that raised the hand, so I open your microphone.
Thanks a lot, and also thanks a lot for the presentation. Daniel here with ABB Corporate Research. I was wondering if you can comment on the power capability of your current cell. I mean, it's a high, it's basically an energy cell, right? You're capable of doing C/12 constantly. Can you comment on power capability? I mean, do you see something more towards going towards C/, let's say 6 or so, such a typical solar or wind energy storage application?
The reason for the development of the STC140 was mainly that the STC250 did a bit miss the goal of the daily cycling applications for supporting of renewable energies. And STC140, it's these C/4 cells which should be perfectly capable of supporting. The funny thing is when you saw the power capability, the cells, I rated with a power capability of 140 watts per cell, and this is really something like the maximum. You cannot get realistically higher, otherwise the temperature does increase too fast. So for the capability is about for this industrial module. For a short time discharge, I allow 19 kilowatts. So for the STC140 container, that's about a 2-hour discharge, but only for 15 to 30 minutes. Yeah. Otherwise, it's better to stay in the 4-hour discharge window, so about 10 kilowatts.
We were probably a little bit fast on that. So we really have today already 2 cells. One is C/12 and the other is C/4. And C/4 is the one that we're pushing most because it covers, let's say, most applications. And if you want really to optimize cost per kilowatt hour, you go then really to the STC250, which is C/12. And to sum it up somehow, on 1 kilowatt hours from the STC140, you need 3 cells for 1 kilowatt hours. And from the larger cell, we need only 2. So this is also where the cost benefit comes from. So we only need 2 ceramics, not 3 ceramics, and so on. Yeah.
Understood. Thanks a lot.
You're welcome.
Also, thanks from my side from the clarification. I think Michael spoke quite a lot about the C/12 cell, so I think that's why we made a bit the link with this cell, or so that the commercialization focus was on this cell. So
no, it's really on the other one at the moment.
It's on the other one even. Okay, so thanks for that clarification. I think now we understand it very well. Yeah, I think if there's no further question, I think we are going to stop the webinar here. Christmas is approaching soon. I would, on behalf of the iBAT Association, thank for all the participation throughout the whole year in the Battery Tuesday. I'm already excited that we have a full program. Please have a look onto our website for the workshop. I think it's very interesting workshop we have at Brucker, and I hope to see some of you already very early next year in Fallanden. So all the best for Christmas, New Year, and a good start to the new iBAT year, or battery year, or whatever year.
Thank you very much, Christian, and same from our side. Have a good time.
Yeah. Bye. Thank you.